This presentation is about the renovations done on the University of Illinois Urbana-Champaign Everett Laboratory, presented by Sophia Saltweedle, Chloe Henkel, Luke Somerville, Sam Hoffman, Nathan Reed, and Gianluca Caruso. Provided on this slide is our agenda for the presentation. We'll first start with Phase 1, the introduction.
Our group represents G2 Builders, a construction company founded in the autumn of 2018 by an ambitious group of young engineers, all alumni of the local Granger College of Engineering at the University of Illinois. G2 primarily operates in the Champaign-Urbana area, and since the company's inception, we've successfully completed projects in a variety of sectors, including commercial, specialized industrial, and higher education. Our talented personnel pride themselves on their integrity when it comes to quality and attention to detail, and we believe no project is too complex for our young minds. G2's mission is to provide a streamlined construction process that delivers the highest quality and most cost-effective project while meeting the most efficient schedule. Clear and open communication with our clients is a key focus point to maintain a trusting relationship and allow peace of mind for all parties involved. Allow me to introduce our team. Nathan Reed taking on the role of Project Executive, Sophia Saltweedle as Project Manager, Chloe Henkel as Superintendent 2, Luke Somerville as Superintendent 1, Gianluca Caruso as Project Engineer, and Sam Hoffman, our intern for the project.
Everett Laboratory sits on the northeast corner of Green Street and Wright Street, directly across the street from Alma Mater statue, the most beloved symbol at the university. The intersection, in close proximity to Boneyard Creek, restaurants and shops, is one of the most traversed on the entire campus, making Everett Lab a very well-known landmark. The lab was originally constructed as the Electrical Engineering Building in 1949. The first class taught in the building was led by William Everett, 2 years prior to construction completion. Before the heating or lighting had even been installed, due to a desperate need for classroom space. The building was renamed in Everett's honor in 1988. In 2015, due to the needs of the rapidly expanding bioengineering department, the 124,000 square foot Everett Lab will undergo a complete interior renovation, replacing outdated equipment with state-of-the-art facilities. Of particular interest is the new Jump Simulation Center, a facility for students of the new Carle, Illinois College of Medicine to access groundbreaking simulation technology and medical equipment for training in a variety of medical settings. Everett Laboratory is scheduled for reopening in June 2018, and G2 is very excited to take on this historic renovation. G2's main objectives in construction are to complete construction on time at the highest quality in the most cost-effective manner possible, minimize effect on day-to-day activities of university students during construction, avoid rework by taking steps and precautions necessary to effectively plan and inspect work the first time around. Also, maintain clear and open communication with all stakeholders throughout the duration of construction. The next topic we will discuss is Phase 2, mobilization.
Signage is used to communicate with the public what is occurring behind the fence. The signage outside of Everett will state that there are renovations being done inside and even list some specific renovations. It will also inform the public that the work is expected to be completed by June of 2018. Lastly, the signage will inform the public that due to construction there may be an increase in traffic at Green and Wright. As you can see, an example of what this signage could look like is included on the right. For the Everett renovations, a site boundary was set up with a post and chain fence. The site boundary is highlighted in red in the figure. The boundary will extend along Wright Street and Green Street but does not include the sidewalk portion in order to avoid disrupting pedestrian flow of traffic. However, the sidewalk on the north side of the building between Everett and Boneyard Creek will be included in the site boundary. This is because by extending the boundary, there is more space available for equipment and material movement. The east side of the boundary will extend past the concrete plaza. However, the main north-south sidewalk between the two buildings will not be included in order to leave space for pedestrians to walk all areas of the quad and use the north entrance of Engineering Hall. Since Everett Laboratory is situated near several busy bus routes on campus, no roadways will be permanently closed off or included within the building site's perimeter. There will only be one entrance on the southwest side of Everett accessible from Wright Street in order to limit traveling on Green Street, which has much heavier traffic. During excavation, there will be a temporary site boundary due to the work being done past the original site boundary. Everything is the same, but the fence on the south side will be further from the building and on the sidewalk to accommodate for the space needed to remove the steam line. It will also extend further to the east as well. These changes are shown in the figure to the right. Once the excavation is completed, the site boundary will be moved back to the original boundaries.
Location for the construction field office will be in the courtyard area to the east of Everett Laboratory and to the west of Engineering Hall. The location for the construction field office is outlined in red in the figure shown. The field office will be a standard office trailer, 60 feet long but 12 feet wide. This location is clear of all construction activities, stationary for the duration of construction, is easily accessible for all construction management personnel, and has a clear view of construction progress. This trailer will be located on the very west edge of the courtyard, diverting minimal foot traffic because the trailer does not block any sidewalks to get to and from the engineering quad to the north. Temporary storage for construction materials will be located above the sidewalk in the southwestern portion of Everett Laboratories property lot. The location for the temporary storage of construction materials is outlined in yellow in the figure shown. The space chosen for temporary storage has enough space to offload from delivery trucks and store for future use. This location is on the northeast corner of Green Street and Wright Street. Delivery trucks will enter off of Wright Street and unload their deliveries in the temporary storage area. The trucks will have enough room to maneuver out of the construction site and exit onto Wright Street.
Trucks needing access to the site will use Wright Street to enter the southwest gate near the temporary storage area. After materials have been loaded or unloaded, the truck will back out of the gate and exit using Wright Street. This route is indicated by the red arrows on the plan shown on the slide. A worker will assist the truck driver in backing out of the site and will be responsible for traffic and pedestrian control as the truck is exiting.
Trucking routes to this site are difficult due to its proximity to the UIUC campus, Campus Town, and downtown Champaign. With these areas surrounding the site to the east, south, and west, the best approach is to have trucks come from the north. No routes approaching from the south or east are shown, and routes coming from the west are shown in red on the map. It was determined that trucks will need to exit off Interstate 74 to avoid these areas. The primary trucking route is shown in green and will have trucks exit from Interstate 74 onto North Cunningham Avenue, turn right onto University Avenue, turn left onto Wright Street, and proceed on Wright Street until they reach the site, shown in blue. The secondary route is shown in yellow, and would have the trucks exit from Interstate 74 onto Illinois Route 130, then continue onto University Avenue. This route requires trucks to exit the highway further from the site. Another alternative route would have the trucks exit onto Lincoln Avenue before turning onto University Avenue, and is shown in orange. This route has trucks exit closer to the site but requires them to make a difficult turn from Lincoln Avenue onto University Avenue. Concrete will not be coming from the highway and instead from Prairie Materials located in Champaign. Since the trucking route for concrete will differ from the routes shown previously, a route specifically from Prairie Materials is shown on the map. The route, shown in green, begins at Prairie Materials, shown in purple. The concrete truck will travel east along Springfield Avenue until reaching Prospect Avenue. Then it will go north onto Bradley Avenue. This allows the truck to avoid underpasses on University Avenue and Springfield Avenue east of Neal Street. The truck will then travel east along Bradley Avenue and return to Springfield Avenue by traveling south along 4th Street. Once back on Springfield Avenue, the truck will proceed east until reaching Wright Street, where it will travel south briefly until reaching the site, shown in blue.
All traffic along Green Street will continue normally, as all trucking routes will travel south along Wright Street to enter the job site through the entrance near the southwest corner of the property. There is a highly active bus stop along Green Street that will not be interfered with. Upon reaching the construction entrance, every truck will then have to pull forward slightly into the intersection of Green Street and Wright Street before reversing through the entrance gate. Therefore, the only necessary traffic rerouting will occur when trucks enter the job site on Wright Street, shown in the diagram with red direction arrows. The crew manning the gate will have to temporarily direct traffic within the intersection upon the arrival of every truck until they successfully back into the site entrance. Similarly, pedestrian traffic will have to be temporarily halted upon the arrival of every truck at the northeast corner of Green Street and Wright Street. Other typical pedestrian traffic can continue as normal along Wright Street as the project's site boundary and fencing does not interfere with the existing sidewalk and foot traffic. Pedestrian traffic along Green Street will need to be temporarily altered during excavation as the site boundary and fencing will extend further south towards Green Street and further east towards the engineering hall to accommodate the removal of the existing steam line. During that time, a considerable amount of sidewalk running along Green Street and the open sidewalk area between Everett Laboratory and Engineering Hall will be blocked off. Pedestrian traffic will have to travel outside of these boundaries. After excavation is over, the site boundary and fencing will recede back behind the sidewalk along Green Street to allow for pedestrian traffic to continue as normal for the remainder of the project.
We will now go on to talk about Phase 3, site work and excavation. Before excavation begins, Julie should be contacted at the following number to have all underground utilities marked and identified before digging. The figure to the right provides the contact information for all of the utility companies that are affected by the renovation. However, all the utility work should be coordinated with the University of Illinois Facilities and Services offices first at the phone number provided.
All existing elements of the gray shaded areas as seen in the demolition plan must be protected before work begins. Handrails marked on the west and east side of the building must be removed. Monuments, stone walls, and light poles on site must be excavated, removed, and stored at an off-site location. Trees as marked on the plans shall be removed, and any other trees on site can be removed as necessary. Shrubs on the west and east sides of the building must be removed also. All walkways located on the north and east sides of the building must be removed. Utilities abandoned in place will be filled and capped. The steam line on the south side of the building shall be removed along with the steam manhole.
There are underground utilities, such as storm pipes, that will need to be removed. An excavator will be required to excavate a trench large enough to remove storm and steam pipes. A CAT 320E crawler excavator has sufficient boom arm length to excavate the required trench depth for storm and steam pipes. Jackhammers will also be required to cut into the sidewalk where a trench needs to be located. Jackhammers will also be required to remove all stone walls, concrete slabs, handrails, and light poles per the demolition plans. A Hercules 15 amp 66 pound 1 1/8 inch hex breaker hammer has sufficient striking power to remove all concrete on the construction site. A backhoe loader will be required to relocate all excavated soil. A CAT C 3.6 backhoe loader has sufficient loader space to relocate all excavated soil from the backhoes. There are numerous trees that need to be removed from the site. Chainsaws will be required to cut down the trees, and a backhoe loader will be required to remove the tree stumps out of the ground. A Husqvarna 32-inch gas-powered chainsaw will be sufficient to cut down all trees on the construction site. A skid steer with drill attachment is required for excavating for the reinforcement piles. A 316GR skid steer has the required amount of operating capacity for drilling for the reinforcement piles. Calculations were made to determine how much soil will be excavated from the site. The soil will be excavated using an excavator, and the soil will be moved off-site using trucks. Most of the excavated soil will be from trenches that were dug to remove abandoned storm pipes. Each trench was dug 5 feet wide and 10 feet deep. The trenches were dug 10 feet deep because 6-inch storm pipes are dug at a minimum of 4 feet below the ground with a minimum 1% slope. The following are the products of the calculations used to determine the amount of excavated soil from digging trenches.
The interior excavation includes drilling 10 to 14 feet for the placement and pouring of reinforcing piles. The skid steer with drill attachment will be entering and exiting from the future side of the roll-up door on the northeast ground floor, and the excavation will begin in the southwest corner at H4, proceeding east as shown to allow the crew to become accustomed to the tight work conditions. The crew will then move to L5 and proceed with the higher risk drilling near the electrical equipment before proceeding along the J column and finishing at L11 as shown in the blue arrows. The shallower new trench, as shown in red, will be excavated after the conclusion of drilling the piles so as not to interfere. The exterior excavation is trenching for new PVC storm piping, 8-inch steam lines, and moving utilities. All soil for this trenching should be used in later backfilling. This excavation will begin in the northeast corner and work clockwise around the building. In doing so, the work nearest critical areas, such as the job trailer and the storage area, will be completed first, so as to not become a conflict of later phasing. The west and east sides can be completed later as they have, the west and north sides can be completed later as they have less potential for conflict.
Additional site preparation may be necessary depending on the equipment needed for the interior demolition and installation. It might be best to temporarily expand a wall to allow easy transport of materials and machinery into the building. This would likely be on the north-facing side of the building, where the entrance already sits at ground level, and an overhead door will eventually be installed.
Upon completion of the excavation phase, all excavation equipment and machinery can be removed from the job site besides the backhoe loader. The crawler excavator will no longer be needed after the necessary trenches are completed. The trucking route used to deliver the excavator to the job site can be used in reverse to return it back to the location it came from. Similarly, the skid steer with drill attachment will no longer be needed and it can be returned along the same trucking route. The jackhammer will no longer be needed after the required demolition is complete. This piece of equipment will be much easier to demobilize compared to that of the excavator, as it can be transported by a much smaller truck, and the truck routes outlined in the mobilization phase do not necessarily need to be used. The backhoe loader used to relocate all excavated soil will need to remain on site after the excavation is completed because the soil will need to be relocated again once the new utility lines are installed. Also, the backhoe loader will be needed to transport other materials on site and to remove any debris throughout the demolition and construction phase. Lastly, the gas-powered chainsaw will not be needed after all trees are removed on site, and it can be transported off-site by any small truck. There are no other materials used within the excavation phase, so the demobilization of any extra material will not be an issue. All operators for the equipment being demobilized will no longer be needed as well.
Next topic we will discuss is Phase 4, Foundations. The foundation of Everett Laboratory is undergoing minor renovations. A new 5-inch concrete slab on grade will be added in the center of the foundation. On the north side of this new concrete slab, a new trench will be added and a portion of the existing slab will be removed for the opening of the trench. On the west side of the foundation, a new concrete wall and new 5-inch concrete slab on grade will be added. A sanitary line will be added on the southern portion of the foundation. Reinforcement piles will be added to 14 concrete columns at locations specified in the foundation plan. Excavation equipment will be needed to excavate all required existing concrete slabs and walls in the foundation. Forms for concrete slabs will need to be constructed and installed where the new concrete slabs will be filled. Liquid concrete will need to be pumped through the northeast entrance of the Everett Laboratory from a concrete mixer to fill the new concrete slabs.
The required amount of concrete must be calculated to ensure that the correct concrete truck or pumper is selected. Concrete is required for the entire new slab on grade, 28 new pile cap reinforcements, and a new 8-inch concrete wall. The new 5-inch slab on grade has an approximate area of 8,590 square feet, which results in a total volume of 3,580 cubic feet or 133 cubic yards. Next, the pile caps are approximately 6 inches in diameter, per the details provided in the plans, and approximately 8 feet in height. Using these dimensions, the volume of one reinforcement pile is around 1.6 cubic feet, or 0.06 cubic yards per pile. Therefore, all 28 reinforcement piles will require approximately 1.6 cubic yards. Lastly, the concrete wall is 8 inches thick, approximately 1.5 feet tall, and 28 feet long. This results in a total volume of 28 cubic feet, or 1.03 cubic yards. Combining all three components of the foundation, a total of 135 cubic yards of concrete will be needed to meet all requirements. Much of the existing foundation will remain during the renovation of Everett. Equipment will be needed to pour the new push-pier pile cap reinforcements, slab on grade, and 8-inch concrete wall below grade. As mentioned within the excavation phase, a skid steer with drill attachment will be used to create the necessary reinforcing pile holes, and the jackhammer will remove the existing slab on grade to make way for the new one. A truck-mounted static concrete pump with a line pump attachment will be used to transport concrete to the desired locations, similar to the image shown here. Multiple trucks are required to supply the required amount of concrete needed as mentioned in the concrete calculations. The trucks can park near the northeast corner of the building, as close to the northeast entrance as possible, so that the line pumps can be run through the entrance and to the reinforcing pile holes and slab. Line pumps will be necessary as there is not a direct access point to the reinforcing piles. Laborers can place and lower the rebar reinforcement by hand into the reinforcing pile holes, which are 3 feet on center from the existing piles and attached by pile brackets per the contractor. The same truck-mounted static concrete pump with line pump attachment can be used to pour the new slab on grade within the building, as it cannot be accessed directly from the concrete truck. Typical formwork and equipment, such as hammers, nails, and lumber, will be used by laborers to prepare for the placement of the concrete.
The phasing plan for foundation work starts with excavating the new sanitary line and trench, similar to what's seen in the top picture on the slide. During this excavation, the formwork for the new slabs and walls can be created. Next, the reinforcement piles for the 14 columns should be placed, similar to what's seen in the middle picture on the slide, and simultaneously any excavation of existing concrete should be done. All concrete except the column slabs should be poured next. Once all columns have been reinforced, the new slab on grade can be poured.
The equipment used for the foundation phase of this project only includes the truck-mounted static concrete pump with a line pump attachment. This concrete pump will be needed for later work in the superstructure phase, as there are new floor slabs to be poured and existing slab openings to be infilled. These activities will require a concrete pump to provide the concrete needed for these pours, as the concrete trucks will not have direct access to the locations requiring concrete. As a result of the concrete pump being needed for later work, it will be best to keep the equipment and operator on the site and have the work on the superstructure proceed immediately after the foundation work is completed. Any material or equipment necessary for the formwork or finishing of the concrete should remain on the site for use in the superstructure as well.
We'll now go on to talk about Phase 5 superstructure.
The renovation of the superstructure of Everett Laboratory involves the placing of new steel framing, laying composite and steel decking on the steel frame, and pouring concrete slabs on the new decking. The steel beams used in the framing are secured with bolts or welding. The first floor requires steel framing to be added to the existing steel superstructure to support the additional weight of the renovation, while the second and third floors require the erection of completely new steel beams and girders with metal decking installation to follow. The second floor, third floor, and high roof require the pouring of new concrete slabs of various thicknesses over new steel decking. All floors, from the first floor to the high roof, require some new slab openings and infilling of existing slab openings, as shown here. New metal stairs will also be placed above the third floor in the northwest and northeast stairwells.
A truck-mounted crane will be required to lift beams through the windows of Everett Laboratory. An IMT 42684 truck-mounted crane with guide wire has sufficient boom arm length for the height of the tallest window at Everett Laboratory. The beams will then be hoisted onto rollers with chains and rolled to the desired location for the beam. Beams will be hoisted into place by a hydraulic beam lift. Since beams are too heavy for manual labor, we will need chains to hoist the beams onto the rollers and a hydraulic lift to hoist the beams into place. A Wesco Industrial hydraulic beam lift has a high enough load capacity for structural steel beams. Welding materials are required to weld the beams and bracing. SMAW, shielded metal arc welding, will be used to fuse the beams and bracing into place. An impact drill will be required to bolt beams and bracings into place.
The superstructure sequencing will begin on the first level and move upwards, floor by floor. Steel framing will initially be stored in the staging area to the south of the building. The truck-mounted crane will therefore be placed on the south side of the building, as shown, where it will hoist the steel through the windows on the south side of the building onto the rollers. The rollers will then carry the beams to the desired location, where the beam lift will hoist it into place. Steel assembly will begin on the first floor and work up floor by floor to the high roof level. Assembly on each floor will move from east to west, as shown. As each floor's steel beams are installed, the steel decking installation will immediately follow. The The concrete portion of the superstructure will follow the steel, starting at the ground level and working up floor by floor. The concrete will be pumped through the south windows using the truck-mounted static concrete pump once the steel decking is installed. On the first floor, which contains an existing slab, the infills will be poured starting in the northeast corner and moving clockwise. On the second floor, the new floor slab will be poured first, and then the infills will begin in the northeast corner and move clockwise as shown. The same will then be done on the third floor. On the penthouse and high roof levels, the concrete infills will be poured moving from east to west. This phasing plan will allow trades to efficiently attack each floor and allow opportunities to begin work on a higher level while lower levels are still working on finishing.
Upon completion of the superstructure installation, almost all equipment can be broken down and removed from the job site. The truck-mounted crane will be needed within the exterior cladding/roofing phase and mechanical phase later on. The rollers and hydraulic beam lift will be maneuvered throughout the building using the elevator. Once all beams and bracing are completed throughout every floor, the rollers and lift will exit the building on the first floor after traveling via elevator and be loaded onto flatbed transport trucks, as shown in the top image. These trucks can leave the job site along any route, as the transport trucks will not be too large. Similarly, the chain hoist will no longer be needed and can be demobilized and transported off-site. Typical welding and bolt equipment can be loaded onto ordinary trucks or vehicles owned by their operators. All superstructure equipment operators will no longer be needed, and they can leave the job site with their equipment once everything is packed away and demobilized. Lastly, there should not be any additional or leftover beams, as they are all prefabricated, but any additional materials such as welding plates or bracing plates can be removed from the site or discarded.
We will now move on to talk about Phase 6, exterior cladding and roofing.
Before work on the exterior can begin, all existing handrails and light fixtures around the building must be protected. There will be a new window curtain wall with metal spandrel panels installed on the south side of the building. All other existing windows will either be replaced with new windows or the openings will be filled with CMU according to the plans. New storefront exterior doors are to be installed. For the north side exterior door, new pan flashing will be installed over the door and new wood trim will be installed around the door. On the south side of the building, a new transom window and insulated coiling overhead door are to be installed. Patches of existing brick veneer and brick masonry will be repointed according to the plans. Remaining exterior doors are to be painted according to the painting schedule. Before roofing work begins, a pre-engineered post and cable fall protection system will be installed for the safety of the workers. The existing limestone cornice around the outer edge of the roof will be repaired and a new metal edge will be installed on top. The roof will get entirely new decking, some parts concrete and other parts steel decking. The concrete roof decking will require new membrane, vapor barrier, insulation, coverboard, and roof membrane. The metal decking will require new rated roof sheathing, membrane, vapor barrier, insulation, coverboard, and roof membrane. A new aluminum skylight will also be installed. New roof drains, rubber interlocking pavers, and TPO walkway pads will be installed according to the plans. New metal panels, gutters, and downspouts will be placed around the building.
The envelope of Everett Laboratory requires little equipment, besides manpower, to renovate. New windows and doors will be installed using laborers. However, a lift will be required to replace windows that are not in accessible areas. A Genie GTH 842 safety lift will be utilized to propel laborers to the correct location of Everett Laboratory to make appropriate renovations. The roof of Everett Laboratory will require safety and construction equipment. A pre-engineered post and cable fall protection system will be used for the safety of the workers working on the roof and skylight. Precast concrete, steel, decking, and limestone will be lifted onto the roof using an IMT 42684 truck-mounted crane with guide wire. Any materials required for sheathing and insulation of the roof will also be lifted by the crane.
The installation procedures for the minor exterior renovations of Everett Laboratory are not too detailed. All windows to be replaced will be installed normally after applying the specified flashing tape, caulk, and sealant as shown in the details to the leveled sills once the existing windows are removed. The existing windows that will be replaced with CMU will be installed following typical procedures utilizing mortar and vertical reinforcement as specified within the plans. All new doors and surrounding trim to replace existing exterior doors will be installed customarily. The most detailed installation will be that of the new window curtain wall with metal spandrel panels on the south side of the building, shown in the elevation view here on the bottom. This wall will be attached to the edge of the slab using aluminum frame connections within the panels and bearing anchors to secure it to the slab. It is crucial that the curtain wall is carefully aligned in its place, as the panels are delicate and they must fit snug between every column. The installation of the new metal deck and concrete deck roofing will be installed with the required membrane vapor barriers, coverboards, and roof membrane as specified in the plans in the roofing plan shown in the top image. The metal decking will be welded to structural steel members using 5/8 inch diameter puddle welds with no more than 12-inch on-center spacing between each, and the concrete decking will be slabs cast on deck. A 49-foot 8-inch aluminum skylight will be installed with 18 skylight bays and a painted guardrail surrounding the opening as shown. All additional accessories such as roof drains or rubber pavers will be installed normally.
For the exterior cladding work, the south and east sides of the building will be completed first, as they face a busy road and walking path and provide aesthetic appeal. The exterior cladding renovation work will start on the south face of the building, then proceed counterclockwise. On each side, the crew will start on the lowest level, then work up the building. After this work, the crew will perform the new exterior cladding work for the penthouse in the same order as the work below. After exterior cladding work is completed on a side, the windows installation will follow the same sequence. For the roofing work, the middle section of steel decking will be completed first. Then the crew will install the steel decking working east to west. This is to allow the glazing crew to work on the skylight in the middle section. Next, the concrete decking will be poured working from east to west. As the roof decking is installed, the pre-engineered post and cable fall protection system will be installed in the working areas as required. Other roofing needs will be addressed following this, like the limestone cornice repairs. The roofing envelope work, including the installation of the membrane vapor barrier and roof membrane, will be completed in the same installation order as the deck. Lastly, the roof drainage system will be installed starting from the east side and moving west.
Overall, there was little equipment required for the roofing portion of Everett Laboratory renovations. Upon replacing all necessary windows for the renovation, the Genie GTH 842 safety lift could be demobilized. The IMT 42684 truck-mounted crane will no longer be needed once all materials are lifted onto the roof and can be transported off-site. Because the IMT 42684 crane is truck-mounted, it is easily transported off-site. The trucking route that was used to deliver the crane to the job site can be used in reverse to return it back to the location it came from. Any additional equipment or remaining materials from sheathing and insulating the roof can be removed from site or discarded.
We will now discuss the means and methods of constructing the mechanical system within Everett Laboratory. The first step of the mechanical system renovation process is the demolition of all existing HVAC components throughout all levels of the building. The demolition includes all major and minor equipment of the prior mechanical system, and weatherproof building envelope enclosures will be required where demolition leaves exposed penetrations in the exterior. Once demolition is complete, the new mechanical system can be installed. For air temperature regulation, the heating system uses pressurized steam from the campus steam tunnels to pass through a condensate return pump in the tunnel level, then move up into a heat exchanger and a glycol heat exchanger on the ground level to heat water and glycol water mix, as shown here. A series of circulating pumps are then used to move the liquids to fin tube radiators and fan coil units throughout the building to provide heat. Other equipment used to regulate the liquids in this system include expansion tanks and air-dirt separators located on the ground floor. Unit heaters are also used, primarily in entrance vestibules and service corridors. For cooling, a water-cooled scroll chiller and a series of air conditioning units are connected to fan coil units. The majority of fan coil units in the building contain only a chilled water coil and are used exclusively for cooling. Electric steam humidifiers are also used to regulate relative humidity in the facility. The ventilation system in Everett consists mainly of air handling units, as shown here, and dedicated outdoor air handling units. These two components regulate air within the building through extensive ductwork with the aid of motorized fans, air filters, diffusers, and exhaust grills. The AHU takes air in from the outside using a supply fan and passes it through a filter to purify it. The air then passes through a heating or cooling coil depending on the system requirement at that time. All exhaust from the system is removed in the process, and the AHU then uses return fans to send the fresh, reconditioned air to the rest of the building through the ductwork. The DOA's units work to assist the central mechanical system by sending air into the system that is less humid than desired. This combats naturally occurring humidity buildup from inhabitants and outside sources, resulting in a comfortable and neutral interior environment.
The equipment needed to complete the mechanical work for this project include a crane, concrete saw, and core drill, as well as scissor lifts. The crane will be the same one from the superstructure work and is needed to lift new equipment into position before the penthouse superstructure is erected. A concrete saw and core drill will also be necessary to cut slab openings in the existing slab locations. The scissor lift will be used to move workers and materials during the rough-in and trim-out work.
As demolition of the existing mechanical system occurs, it's important to confirm that all equipment has been safely and permanently disabled. Safe demolition practices, such as closed debris chutes, should be used throughout this process. A weatherproof building envelope must be installed where demolition leaves exposed penetrations in the exterior. Shrink-wrapped Durock cement board, sealed properly with caulk, should be sufficient, unless significant openings require temporary enclosure construction. The equipment installation will be carried out by the truck-mounted crane, which will lift all mechanical equipment meant for the mechanical penthouse level directly from the staging area. Workers will carefully guide each component into its final position. This will streamline the installation and connection process for HVAC technicians. Fan coil units are installed throughout the building on the ground level, second floor, and mechanical penthouse level. An FCU is an air handling unit that is not connected to the mechanical system through ductwork, instead heating or cooling a specific area. The FCUs in this project are installed following the erection of the superstructure and do not require the crane for placement. The FCUs are hung from blocking, requiring coordination while framing the building to ensure blocking is in the appropriate locations. The FCUs will be lifted into the appropriate location using a scissor lift and then fastened to the blocking.
The first portion of the mechanical work that will need to be completed is the coordination with other trades. This starts with coordinating the safe demolition of the existing mechanical system. During the superstructure work, the mechanical equipment needs to be lifted into location on the mechanical penthouse level, and slab opening locations need to be coordinated in the new and existing slabs. The last portion of coordination that we want to emphasize is coordination with framing and drywall regarding having proper blocking for the FCUs and ensuring that mechanical rough-in work is completed prior to the installation of gypsum board and acoustical sealing. The next phase is equipment installation. As mentioned previously, the AHUs and DOAs will be lifted to the mechanical penthouse level using the truck-mounted crane. The FCUs will be installed in the appropriate locations on the ground floor, second floor, and mechanical penthouse level using a scissor lift. The distribution elements will be installed following the equipment installation. This work will start on the ground and tunnel floors in Area A, then move to Area B, then to Area C, and end in Area D. The long continuous ducts in the hallways and large rooms will be installed first. Then the smaller branches will be installed as appropriate. This mechanical rough-in work will need to be completed before plumbing and electrical rough-in, as to not have any conflicts. The mechanical trim-out work will follow the completion of the rough-in. The trim-out work includes the installation of thermostats, sensors, return vents, supply diffusers, and air intake louvers. Most of the trim-out will be completed prior to plumbing and electrical trim-out, except for the installation of thermostats and sensors, which will occur after painting. The trim-out work will follow the same sequence as the installation of the distribution elements, starting on the lower levels, then working up the building and through the different areas on each floor. After trim out is completed, the mechanical system is ready for test and balance, which needs to be coordinated with plumbing and electrical.
Mechanical system construction requires small mobilizations and demobilizations between the true start and finish of work due to the necessary order of construction for MEP systems. The mechanical construction begins with placement of large equipment, followed immediately by mechanical rough-in. Between rough-in and trim-out, however, the mechanical trade must pause to allow drywall and acoustic ceiling tiles to be installed. Other trades will continue to use the truck-mounted crane and scissor lifts, so this equipment may remain on site. Once the walls and ceilings are in place, workers commence the mechanical trim-out, installing components such as air intake louvers, return vents, and supply diffusers. Then, another short demobilization is required while electrical and plumbing trades complete their trim-out. This is followed by final finishes, such as floor trim and painting, after which mechanical returns for the last time to install fragile equipment, such as thermostats and sensors, and begin testing. Once the mechanical system has been completely constructed, tested, and balanced, final demobilization can begin. At this time, the only remaining work is punch lists and final cleaning, so the truck-mounted crane and scissor lift will leave the facility unless they're needed to address an issue in testing. Any remaining mechanical materials will be disposed of or transported off-site, and final startup can begin.
We'll begin to wrap up our presentation by talking about the final phase, Phase 7, framing and interior finishes.
The framing needs for the renovation of Everett Laboratory includes enclosing the ceiling and interior walls. The ceiling will be enclosed by either acoustic ceiling tiles or gypsum board according to the plans. Interior walls will either be gypsum board or masonry walls. The types of gypsum board used are A, B, C, D, E, F, S, and SS. The most common types used throughout the building are A and B as shown in the picture. Masonry wall types are M and N. The X next to each type denotes the metal stud size in the plans. Interior door frames and doors will also be installed. Interior finishes includes light fixtures throughout the building to be installed according to the interior plans. All restrooms in the building require accessories such as soap dispensers, mirrors, paper towel and toilet paper dispensers, and hand dryers. Stairway railings and guardrail extensions will be installed and painted to match the existing. Office and classroom furnishings include chairs, desks, tables, whiteboards, shelves, and cabinets. Additionally, projectors and mounted screens need to be installed in classrooms. Lab furnishings include lab benches, fume hoods, lab sinks, and emergency showers. Flooring finishes includes carpet tiles, plastic laminate, porcelain tile, vinyl composite tile, rubber flooring, resinous flooring, and resilient flooring. There are several specialty furnaces needed for Everett Laboratory. For the research labs, this includes biosafety cabinets, carbon dioxide incubators, refrigerators, freezers, ice machines, autoclave chambers, and cold room control. The classroom labs require biosafety cabinets as well, a bench press, and treadmills. The repository needs LN2 cryogenic storage and specialty freezers. The simulation center will require extensive medical equipment, including stretchers, surgical lighting, IV poles, and ventilators.
The main equipment needed for completing this interior work will be scissor lifts. The site will have Genie GS slab scissor lifts available for the trades to use. The framing, drywall, taping, painting, and interior finishes crews will use these scissor lifts to lift workers and materials for installation. Paint rollers will be used for most of the painting. Painting of the drywall will be completed using rollers, so no additional equipment will be required for this task. As for the metal fixtures, the painting of the metal stairs and handrails will be done using a paint sprayer to allow even coats of paint to be applied to the metal components, ensuring a clean finish.
All interior finishes will be installed before exterior finishes at Everett Laboratory. The exterior finishes will be installed last to make it easier to bring materials into the building. All interior drywall will be installed from the bottom floor to the top floor. The walls will be covered before the ceilings on each floor. All flooring finishes, carpet tiles, plastic laminate, porcelain tile, vinyl composite tile, rubber flooring, resinous flooring, and resilient flooring will be installed after the walls and ceilings are covered in gypsum board. All specialty furnishes will be installed in the following order: research labs, classroom labs, simulation labs, bathrooms, and conference/office rooms. The laboratories will be furnished first because most finishes are heavy and clunky, which will take longer to move from one place to another. After all specialty furnishes are added, then light fixtures will be installed. After all interior furnishings are added, handrails and guardrails will be installed to all stairs on the site. The last items installed will be door frames and doors. After all installations are complete, all walls and ceilings will be painted.
Being a renovation, there is not much equipment needed for framing and interior finishes. The Genie GS slab scissor lifts provided on site for all trades can be demobilized once all interior work is finished. The lifts can be transported off-site using flatbed transport trucks along any route shown here in the diagram. All laborers and extra material, if any, will no longer be needed either.
Thank you for watching our presentation, and we at G2 Builders look forward to beginning this historical renovation.